It is part 2 of section 2.3. In the first part, we studied the Newton's method. The Newton's method is a powerful technique. However, it has a major drawback. As you can see here, it requires to evaluate derivative of f at each iteration. In many cases, derivative evaluation is much more difficult and expensive than function evaluation. So in order to overcome the drawback of the Newton's method, various methods have been proposed. One of the most popular variants is the secant method, in which the derivative is replaced by a difference quotient, which is formulated from the last two approximations. So the resulting algorithm is formulated as in this equation. Here f prime pn minus 1 is replaced by this quotient to get this one. Now n is now larger than or equal to 2. You can update from P2, and P0, P1 must be given. But this requirement is not a drawback. Finding an accurate P0 may be difficult. However, getting another initial value P1 is not so much difficult. For example, after getting P1, you may perturb it to get P1. That's it, quite simple. In each iteration, it requires only one new evaluation of f. Because we can save the evaluated value, then in the next iteration, this value will be used for that position. So in each iteration, we need only one new evaluation of f, and we don't have to evaluate derivative. So in some sense, in each iteration, the computational cost is about half the Newton's method. However, this new method has a slower convergence than the Newton's method. By using an error analysis, we can reach at this estimation. En magnitude is about now this quantity, and En minus 1 magnitude to the this power. Its numeric value is about 1.6. Newton's method has quadratic convergence. This one has 1.6 convergence speed. Secant in each iteration, it requires a smaller number of operations, so that overall, the secant method is not bad. In many applications, the secant method is faster than the Newton's method. The graphical interpretation of the secant method is similar to that of Newton's method. The secant method utilizes the secant line. That's the reason we call it secant method, while Newton's method updates the iterate through the tangent line. Let's see a graphical interpretation of the secant method. We choose a simple function, x cubed minus 1, so that the root p is 1. Now, by using a built-in function of maple, we choose P0 is 1.5, P1 is 0.5, and we do 3 iterations, output this sequence. So here P0, P1, P2, P3, P4, it looks converging to 1. Right? Let's see, plot how they are computed. Okay, here A is 1.5, which is P0, that one, and B is 0.5, that is P1. Now, on the graph, that is P0 point and there's P1. We connecting them. We connect them and take x-intercept. That is new value P2. And by using P1 and P2, the 2 points on the graph, we connect them and x-intercept. That's now U1, P3. And from P2 and P3, we consider the points on the graph and connect them and the x-intercept. That is again P4. The secant method is working in this way. This is a graphical interpretation of the method. You may try to solve this problem yourself. Now, we'll consider another variant of the Newton's method, which is called the method of false position. The method is quite similar as the secant method. However, the method includes a test to ensure that the root is always bracketed. We'll see how the method is working. P0, P1, the initial two values are chosen such that f of P0 times f of P1 is here negative. That means that P0, P1 are chosen such that P is between them. Okay, let's see here this picture. So P is here, then we choose initial value P0. One is on the left hand side, and the other one is on the right side, like that. So that here that's a P, and then here maybe the graph of function, graph of f is given in this way. Then now the value over there is negative, the value over here is positive, so that is satisfied. Okay. Now here, in getting P2 is exactly the same way as for the secant method. We consider the secant line joining these 2 points and x-intercept, which is P2. Okay, so that is now P2. After that, and here we test and f of P1, f of P2 product less than 0. Okay, in this picture right now, f of P1 is positive, f of P2 is positive, so that it's not satisfied. That means that P is not between P1 and P2. So we ignore that. And then, now we are using this one. So we consider now here for P2, that is new value, so the new point, and now secant line is made from this point to that one, P0, P2 and P0. So that here we are using this secant line, and now P3 is made for that one. So here the manner is that, okay, by using P0 and P1, we get P2 here. And now to get, okay, that is P3. To get P3, we check if the solution is this side or that side. So that once the solution is in this side, then, and here we are using these 2 points to get the secant line and x-intercept. So the menu is a little bit like bisection method. When we are choosing half interval, and we choose the half interval so that the p is inside, but this is not half interval. However, here we are choosing the part where the root is so that, and this method can be considered as a combination of the secant method and bisection method. Okay. Here for this one, for that function, we start with here now P0. Okay, let's see here now. That is P0, and this is P1. Now P2 is gotten just simply connecting these 2 points and x-intercept. Now we test here P is which side P is, but this side there's no P and this side has P, so that we are using these 2 points, so that corresponding graph point is these two, and here we get that is P3, right? Now here last 2 is this one, and then P3 appears as a new point, and we test again if the solution is this side or that side. Right now solution is this side, so that we are using again here this point and that point to make the secant line and x-intercept, which is the new update P4. In this way, the solution is updated. So it is really a combination of secant method and bisection method. Okay, we compare here convergence speed, and we try to get root of x equal cosine x, start from here pi over 4, or now, and that's for Newton's method, but for secant method and false position method, from this one we perturb a little bit to get 0.5, so that we compare the speed of convergence for 3 method and same conditions except only this initialization, and we compare the convergence. Now this is a Newton method and secant method and a fourth position method, and here there is a 10-digit accuracy, and after 3 iteration, and now it's not changing, so that the error becomes now less than 10 to minus 10. Now for secant method and false position method, here after 5 iterations, and now it is convergent. So it requires about twice iteration. However, in each iteration, the secant method is now taking half course the Newton's method, so that eventually overall the computation time is more or less the same. In many cases, secant method is faster, and false position method is around the secant method. Some people like that, but in higher dimension application, usually secant method is used. Okay, that's the end of section. Thank you.